Now we are going to calculate some limits using the squeeze theorem. The squeeze theorem states that is if f is between g and h, and both g and h approach the same limit L as x approaches c, then f will be squeezed in between those two limits also to approach L as x approaches c. The main purpose of the squeeze theorem is to prove the following trig limits that you see to the right. So let's just go ahead and get into some examples of using these special trig limits that were calculated using the squeeze theorem. So in example A, we want to evaluate this limit. The limit as x approaches, or theta approaches 0, of sine 3 theta over theta. So when I look at this limit, sine 3 theta over theta, as theta approaches 0, it looks very similar to this limit. The limit as x approaches 0 of sine x over x will equal 1. So we ask ourselves, how can we manipulate this trig limit so that it looks more like the special trig limit on the right that we know is equal to 1? Well, I know that this is sine of 3 theta. So if I multiply this by 3 on bottom and on 3 on top, now I have the limit as theta approaches 0 of 3 times sine of 3 theta over 3 theta. This is looking a lot more like that trig limit. I'm going to do a little substitution though to make it look even more like that limit. If I let x equal 3 theta, then as theta approaches 0, x will also approach 0 because I'm just plugging in 0 for theta. So now if I substitute this in terms of x, I have the limit as x approaches 0 of 3, because this 3 didn't change yet, times sine of x over x. So remember that this constant can move in front of our limit now, and we have 3 times the limit as x approaches 0 of sine x over x. And we know that the limit as x approaches 0 of sine x over x is 1. So this overall limit is 3. Now I know that this method might seem involved, but we will ultimately turn this into some shortcuts later. But right now we're deriving it in a longer fashion. So now let's continue on to part B. This is a more elaborate problem. We've got a few limits going on. I see we have the multiplication and division. So what I can do is first look at this as kind of 3 different limits. Limit as x approaches 0 from the right of sine 2x multiplied by the limit as x approaches 0 from the right of cosine 5x divided by the limit as x approaches 0 from the right of tangent 8x. So I am doing this very, very worked out in a long formal fashion. We will turn this into shortcuts later. So first, as x approaches 0 of cosine of 5x, this is going to approach 1. So we don't need to worry about that limit anymore. However, limit as x approaches 0 of sine 2x and tangent 8x look very similar to this limit on the right, here, and here. How can we make these limits look more like these special trig limits? Well, sine 2x, I can multiply this by 2x over 2x. And tangent 8x, I can multiply this times 8x over 8x. So now we have the limit as x approaches 0 from the right of 2x times sine of 2x over 2x, and we remember that other piece is 1 already, divided by the limit as x approaches 0 from the right of 8x times tangent 8x over 8x. So we've just shown in the limit to the left that once you have sine of something over the same value or tangent of something over the same value, those will be 1 if we did some substitution. So this is the limit as x approaches 0 from the right of 2x times 1 over 8x times 1. What's going to happen now are these 1's cancel, these x's cancel, and we're left with the limit of this constant fraction 2/8, which simplifies to be 1/4. So if you thought that these were crazy, they are, because I'm showing you the very formal way to derive these limits. We will create shortcuts.